Hello and welcome to this video. So in today's video we are going to discuss about the superfluid transition of liquid helium and lambda transition or lambda point. So what is liquid helium? We have already discussed in one of our previous videos, the link to which I will give here in the I button. So today we will discuss about this transition, this phase transition of liquid helium. Okay, so what does it mean? What does it refer to? It refers to the phase of helium, superfluid. We are talking about the superfluid phase. The phase of liquid helium in which at very low temperature it flows without any viscosity. Meaning, superfluid means that particular fluid has no viscosity. It can move through tiny pores, climb walls and remain motionless when its container is spun. Okay, now this who observed this first superfluidity effect? It was first observed by Piotr Kapitsa, John F. Allen and Don Meissner in the year 1937. And this particular person, scientist, he was a Soviet scientist. Piotr Kapitsa was also awarded Nobel Prize in Physics for his work in low temperature physics. Okay, so I hope you understood what is this. So these are some of the characteristics of a superfluid. Okay, so this is the phase diagram of liquid helium. We also discussed this one in the previous video, one of our earlier videos of on liquid helium. So this is called something called lambda line. To the left of lambda line is helium 2 phase, which is the superfluidic phase, and to the right of the lambda line is the helium 1 phase, which is the normal phase. And this transition happens here at this particular temperature, which is nothing but 2.17 Kelvin. Okay, of course this spot is between temperature and pressure, and this is the point where the transition happens at 2.17 Kelvin. Transition means transition from helium 1 to helium 2, where helium 1 is a normal fluid and helium 2 is a superfluid. Okay, so now again, what is the lambda point? It is observed in helium 4. We have already discussed the lambda point here, which is 2.17 Kelvin here in this particular picture. And we observe this lambda point at normal pressure, which is 1 atmospheric pressure. Okay, at 1 atmospheric pressure we observe this lambda point, normal pressure. Okay, so now the question is, why is it called lambda point? It is because of the peculiar looking graph of what? Temperature versus the specific heat of liquid helium 4. Okay, the name comes from the shape of the graph of specific heat, temperature and liquid helium 4 at 2.17 Kelvin. As we have already discussed, it resembles that of Greek letter lambda. Okay, this is the graph which I also showed you on the thumbnail. So you see the graph is okay, along x-axis we plot temperature, along y-axis we have plotted specific heat. So the specific heat increases like this, it keeps on increasing, and at this transition temperature 2.172 Kelvin is the transition temperature or the lambda point. Here this specific heat shows a very discontinuous change. Okay, very discontinuous change, and this particular graph here, it is increasing like this and then it's decreasing like this. Doesn't it resemble with that of the Greek letter lambda? You see here lambda, it's going up, like here it's going up, but the lambda is a bit curved here on the top, but here it is not curved, here it is straight. But here you see, then again it comes down like this and splits like this. So you now compare it with yourself with this Greek letter lambda. So this above the critical temperature, the specific heat changes like this. So I hope by now you must have understood why this particular graph of specific heat versus temperature for liquid helium is called a lambda plot or a lambda graph. Now the question is, why this is so, why this graph looks like so. So it is a second order phase transition. So what is the order of phase transition? That also we already discussed in our previous video, the link to which I will give you in this I button. And then superfluid helium has extremely high thermal conductivity. Okay, that is why its specific heat keeps increasing up to the transition point. The lambda transition is associated with the change in the symmetry. This is the reason why I observe the lambda transition, because that is the change in symmetry and order parameter of liquid helium. Okay, change in symmetry and order parameter. Remember these two terms. So for normal helium 1 has different symmetry than superfluid helium. Okay, normal liquid helium is to the right. It has different symmetry as opposed to helium 2. Okay, different symmetry and different order parameter, and that is why we observe the transition in the specific heat like this continuous graph, which is also called as lambda plot. So I hope today's discussion has been clear. We have discussed about the superfluid transition. It happens at 2.172 Kelvin temperature, and the specific heat versus temperature plot looks like that of Greek letter lambda. That is why this particular plot is also known as lambda plot. So friends, this was all about today's topic, today's discussion. I hope you have liked this video and this will be also beneficial to you. Thank you very much for watching this video. If you have not subscribed to the channel, please subscribe. I will soon upload another interesting video. Thank you very much, and I will see you soon.